Hey everyone, let's get started. Or maybe I'll wait a sec. Okay, so welcome back after fall break. Hopefully everyone had at least somewhat of something relaxing. So a few quick announcements. So homework 3 is going to be due next Tuesday, but if you haven't opened it yet, please note that the conceptual part is due by Monday at class time. So Monday, we're gonna turn off that questionnaire for the conceptual part on Monday. Sort of related to that, please come in person on Monday and bring a laptop or like a phone or something so you can do like Slido quizzes or something like that. On Monday's class will probably not be recorded. It might be recorded, but certainly sort of you won't get much out of it because it's mostly going to be a class discussion and things. So please like prepare to be like in person and talk on Monday. Definitely won't be posted online. The following Monday, we're not going to have class. There's some traveling and a few logistics things. So we're going to replace the following Monday with a guest lecture at some other to be decided time. You're not mandated to show up live on that guest lecture because it'll be at a non-traditional time, but we'll announce all of that later. Please note the office hours. So Zhe is going to do extra office hours on Friday to make up for yesterday's office hours that were during fall break. And then finally, for those of you who have been following the due dates on the calendar online, we're about to update them. They're sort of everything for the remainder of the class besides homework 3 is going to be pushed back a little bit just to give some more breathing room to like spend more time to cover some of these topics. Friday is a maker day. Okay, I'll think about what that means and okay, cool. Any other questions or comments? Okay. Cool. So let's get started with the extra material then. Okay, so I know recently for like pricing, we've covered like the material has been quite theoretical and technical. Today is going to be the last day of that. We've been in the weeds. We're going to remain in the weeds for about like 70% of this lecture, and then we're going to start popping back out to start getting the bigger picture on pricing and algorithmic pricing. And then next week, not on Monday, but on Wednesday, I'll do like an extended case study on like pricing in online marketplaces. So if like the weeds that we've been covering is not your thing, please bear with me for about half more of a lecture. This is important stuff, which is why I'm covering it. Okay, so what have we done so far? What we've done is how to do pricing in if you just have one time period and you're selling a single item. You have some demand distribution, which is how much the fraction of the population that's going to buy a good at a certain price. And then given that demand function DFP, we talked about how to do revenue maximizing pricing. We also talked about how to estimate this demand distribution by plugging in various machine learning models in different forms. And then last time, we talked about how to think about capacity constraints over time. And here we introduce what's called dynamic programming or Bellman equations. And here, the idea is that if you have T time periods to sell an item, you want to maximize expected revenue. The question is, what prices do I set for each time period? What price do I set on time 0, time 1, all the way to time t minus 1? And the key idea is that I can't know what price to set on day 0 unless I know what happens if I fail to sell the item after day 0. And I can't set the price for day 1 unless I know what happens if I fail to sell the item on day 1. And what happens if I fail to sell the item on day 1 depends on my prices P2 all the way to... Hello? Ja, can you kick out anyone who happened? I don't know how they entered the room. Okay, cool. That's why we don't allow remote lectures, remote attendance. Okay. Okay. So yeah, so the key idea is that you can't optimize your day zero prices unless you know what's going to happen after day zero. And so you start backwards. First, you decide your very last price. Like what happens if I just have one more day that today's the last day to sell the item. And then given that, I can decide what price I do the day before and so on. I've posted additional notes on this. Sort of, I realized the sort of what I covered in the last class was a little terse and sort of like how the equation actually collapses. So I posted some additional notes that sort of writes down the full revenue equation for like 3 time periods and then shows how it collapses into the equation that I showed on the slides last time. And I'm happy to go over that in more detail. Sort of might have some time at the end of the lecture to like do some writing on the iPad. Otherwise, please come to office hours for additional questions. Are there questions here before I move on? Okay. Okay, so what's the plan for today? So sort of I just covered what we did last time. We did a little bit more on demand estimation, like how to use user and item vectors. And then we also did capacity constraints over time. And again, sort of the name of the game for this module has been peeling back more and more assumptions that we made on the first day with revenue maximizing pricing. So we still had a bunch of assumptions from last time. We just had one type of item. We could have potentially had many copies of it, but we only had one type of item. We were allowed to explicitly give prices to different users, or different prices at different time periods. And we also had no competition. And then there was a few other assumptions. And today we're going to start like thinking about how do you deal with sort of when you don't make some of these assumptions. And then sort of, so especially sort of for the majority of like the brunt of the content for most of this class, we're going to think about if you have multiple kinds of items to sell, how do you sort of figure out jointly prices for multiple kinds of items? And how do you think about doing demand estimation? Sort of like how do you plug in arbitrary machine learning models to do demand estimation when you have multiple kinds of items? And then sort of the end of the class, I'm going to start putting all the pieces together with like everything we've done with pricing so far. And I'll do that by introducing sort of the class project, which is going to be sort of most sort of like, started basically the only assignment starting in like November 10th or something, like sort of early November through the end of the semester. That'll be sort of the class project will be the only assignment. And so I'll start introducing that, and that'll start putting the pieces together on recommendations, pricing, and a little bit on experimentation, which we're going to start covering not next week, but the week after. Okay. Okay, so let's think about selling multiple kinds of items and how to do what's called price differentiation. So the example I want you to have in mind for like sort of the content that I'm going to cover for the rest of this class is what happens when you're selling, for example, an item with multiple possible quality tiers. So this is for those of you who've used Uber before the pandemic, the ride-hailing used to offer at least multiple tiers of service, right? You had pool, which is, you get in a car with a few other people. You could have Uber X, which is sort of your own person, like sort of no other customer gets in the car with you. You also had Express Pool, which is like pool, but you potentially had to walk toward the car. And so these are 3 different items that Uber is offering you at the same time, and you could decide which one of these items you want, if any. Right? So, and the quote unquote worst quality items are also cheaper, and they also cost less for the platform to deliver. Right? It's cheaper for Uber to do a pool ride than it is an UberX ride. And so the question is how does the platform set the prices for these things together, right? Or if you're a large retail platform and you're selling 100 items, how do you jointly price all of these things? Okay. And so to maybe start thinking about why this is a non-trivial problem, let's think about what happens if you just set the revenue maximizing price for each item separately. Sort of, can people think about what are what are problems if I just ignore the fact that I have multiple items? Any thoughts? Yeah. So okay, great. So one of the answers was you might cannibalize some of the demand for one product with another. And yep, that's exactly right. And I'm going to talk about some of that that in detail later on in the lecture. What are some other challenges? Any thoughts? Okay, so we'll keep it there for now, and then I'll introduce some more things later on. Okay, and so maybe as an illustrative example of the cannibalization that we just sort of at least briefly mentioned is what happens if we make Uber Pool cheaper. So if we keep the prices for Express Pool and UberX the same, and you just decrease the price of Uber Pool, what happens? What would probably happen is more people would start using Uber Pool, but that comes at a cost for people who are using UberX. And so if the platform is making most of its money on UberX, which is, I don't think, true, but if that's sort of, then they would actually end up potentially losing money even though they're selling more items. Or even if they're making more money on Uber Pool overall. Okay, so that example, let's just generalize this example a little bit to think about the motivation for what we're going to do. So the first one is just simply, for whatever reason, you have a bunch of different items to sell, right? You have different types of clothes, or different types of laptops, or a plane has different types of seats because of how it was constructed, right? So for whatever reason, you have different types of products that you're together trying to sell, and customers are probably just going to buy one of them. The second motivation is, I think, a little bit more subtle, which is it's a way to do what's called price differentiation without giving different people different prices. So what I mean is that earlier we talked about personalized pricing with covariance, right? A customer walks in, you see that they're super rich, and so you increase the price on them, right? So your pricing, you explicitly gave different customers different prices based on things that you knew about them. In many settings, that's not possible, either technically, legally, ethically, right? For a variety of reasons, we might not want to explicitly show different prices to different people. But at the same time, you might know that there are sort of, if you could give different prices to different people, you would make a lot more money, right? And so the way around that is selling different items with different tiers of service, right? So the idea of a business class seat in an airplane is there's some people who different people have different trade-offs for quality and cost, right? Some people are very happy paying, what are the $1,000 extra for a business class seat, when they could have also gotten on the plane with an economy seat. And for some people, that's just a no-go, right? I'm never going to pay that much money out of pocket for a business class seat. And so the idea now is that with higher or lower tiers of items, you can extract more money from the people willing to pay for the higher tier while still earning a little bit of money from everyone else, right? So it's a form of personalized pricing without literally giving different prices to different people. You just give different quality items, and then you allow people to self-select into the item that they want. Any questions about the motivation here? Okay. Okay, so what are the challenges here? The first one, as I'll get into in a little bit, and as I've already mentioned, is now the prices depend on each other, right? Is you can't optimize the price of Uber X without also thinking about what you're going to price Uber Pool, and vice versa, right? Because you need to think about these two things jointly. And one of the big reasons you need to think about these two things jointly is what's called cannibalization, right? Is you don't want people who would have bought the luxury good if that was the only thing that you offered to instead opt into buying the cheaper thing because it's available, right? So you need to be careful about like offering the cheaper goods such that certain people buy it without without inducing the people who would have paid more money to pay less money. Okay. So with that introduction, let's start thinking about the model and how you would go about doing this. So in the example, sort of throughout, let's just suppose you have two types of items. Everything I say would generalize to how many other items you have. But let's just suppose you have two types of items. And let's say that each customer that walks in is going to buy at most one item, right? Someone's not going to buy both a business class seat and an economy seat for one person, right? And sort of the way they're going to buy the item is as follows. Each person so earlier a person had a valuation, V, for just like that single item. Now the person has a different valuation for item one and a different valuation for item two. And each of these can be personalized. Okay, so they have valuations V1 and V2. Okay, and now suppose you set prices P1 and P2 for item 1 and 2 respectively. In the class, what I'm going to cover is the following way that people are going to make decisions. So I'm going to say that the utility that someone gets out of buying the item is their valuation or minus the price that they pay. So if I internally value the item at $100, but I have to pay $90 for it, then I only net $10 of utility, right? So the utility I get from each item is my valuation minus my price. And I'm going to claim, or sort of what we're going to assume is that the person makes the decision based on the valuations for the two items, or sort of this utility for the two items, VJ minus PJ. So the person is going to buy neither item if both of the valuations are less than the prices offered, right? So this is exactly the same as we had earlier, where if my price is more than I value, then I'm not going to buy it. But now, if suppose one or both of these are above the valuation, how am I going to assume which item you buy? I'm just going to compare these utilities. So if V1 minus P1 is greater than V2 minus P2, then I'm going to buy item 1, right? Because my utility for item 1 is more than my utility for item 2. And if V2, or on the other hand, if V2 minus P2 is greater than V1 minus P1, then I'm going to buy item 2 instead. Right? So all I do is I compare these valuations, or these utilities, and then I decide which item to buy. And what I want to point out here is that this is like a fairly strong assumption on how people make decisions, right? So there's a lot of research in behavioral economics, but sort of also in operations research or game theory and sort of all sorts of things about, and also like learning, sort of even machine learning about how people actually make decisions, right? So you could imagine that people make decisions randomly, and they make decisions randomly with a probability that depends on these utilities, right? So if like two utilities are very close to each other, I just like flip a coin. But if they're far apart, then I pick the higher one. Here, sort of throughout, we're just going to assume that people like make decisions deterministically based on like, you know, whichever utility is higher. And the assumptions that you make here actually will change your pricing quite a bit. Like, you know, the general methodology will be the same, but sort of your prices will look different. But yeah, that's an aside. If like this is something you're interested in, the things to look up are what's called consumer choice models, because it's a model for how consumers make choices between different items. Okay. Any questions about sort of the model before we think about pricing here? No questions? Okay. Okay, so let's like look at this in a little bit more detail. So what the image is on the x-axis, I have valuation. So sorry, V1, the value. So this is a 2D plot where each person is in one location on this plot. And the x-axis is like their value for item 1. And the y-axis is their value for item 2. And so each person is going to be one dot here. And then what I have, what I've drawn is, suppose I put price 1 sort of here where this green vertical green line is, and suppose I put price 2, price of item 2 in this horizontal line. So like this is just visualizing the decisions people make. So and let's look at this a little bit more. So in this yellow region, I claim that in this yellow region, people will buy item 1. Why? Because in this yellow region, value 1 is greater than value. So let's look at this square first. In this square, value 1 is greater than value 2. Value 1 is greater than price 1, but value 2 is less than price 2. So in this square, sort of the only option is to buy item 1. In this white square, both of my valuations are less than the prices, and so I'm not going to buy anything. And then we have to think about what happens in this square. In this top right quadrant, both value 1 is greater than price 1, and value 2 is greater than price 2. So if either of those items were offered alone, I would just buy either of those items. But since they're offered together, I need to compare which one's higher. I need to compare whether V2 is minus P2 is bigger than V1 minus P1 or vice versa. And it turns out sort of you can draw sort of a line at the 45-degree mark, and sort of everywhere above this line, people will buy item 2. Everywhere below this line, people will buy item 1. So this is just visualizing the decisions we make. This is convenient to think about like the joint implications of like pricing and like revenue maximization. Any questions about how to read this? Okay. Okay, so how much money do I earn? So let's suppose I have some set of prices, P1 and P2. Then just for a little bit more notation, let demand sub 1, so demand subscript 1 be the fraction of people who buy item 1. And so in this plot, it's going to be the fraction of my customers who live in the yellow region. Same thing, demand subscript 2 is sort of the fraction of my customers who live in the blue region. And then what is my revenue? My revenue is just price 1 times the fraction of people who buy item 1 plus price 2 times the fraction of people who buy price 2. Okay, and so given these two functions, given demand 1 and demand 2, we can optimize, we can find the optimal prices through, in this class, we're not thinking about like closed form optimization solutions. We're just like, through brute force and code as you're doing in homework, you can find the optimal prices 1 and 2 by just sort of testing this revenue function at every price 1 and price 2. Okay. So what does it mean to cannibalize now? What it means is, okay, and so this is how prices affect each other, or prices affect the other item. So here's my revenue again, the same thing I had in the last slide. Now, suppose I decrease the price for item 1, right? So I decrease P1, and so what I do in this plot is I move P1 to the left. Then what's going to happen? I make less money in the yellow region, right? So for someone who's in the yellow region, I make less money off of them because P1 is not smaller than it was before. And that's bad for my revenue. But at the same time, this yellow region is becoming bigger, right? So the same thing with one item. If I decrease the price of a single item, more people buy it, but I make less money per sale. And so now again, the yellow region, with decreasing the price, this yellow region is going to become bigger. And sort of the first effect of the yellow region becoming bigger is that the white region becomes smaller, right? Sort of the number of people who purchase nothing now goes down. And that's a good thing because now I'm making some money off people who earlier I was making no money off of. But also the blue region is becoming smaller, right? So if I sort of move this to the left, sort of there's going to be more people here, sort of this line also shifts, and the yellow region here is going to become bigger at the expense of the blue region. And another way to say that is if I sort of this demand D1 is going to go up, but it's going to go up at the expense of D2, right? So the number of people by item 2 will go down. And this is the cannibalization effect, right? That now I'm making, so now more people are buying item 1, but that might come at an expense of the number of people buy item 2. And so when I think about how to jointly price P1 and P2, I can't just do this independently because sort of they're connected through the demands. Okay, any questions here? Yes. So throughout this entire module, I'm a little bit like hand wavy whether demand is like a fraction or a number, like sort of the number of customers. Here, I've been mostly thinking about fractions, yeah. But you could imagine sort of I just multiply this entire thing by like n, which is like the number of customers who could think about. And the reason I want to sort of think about fractions is fractions are nicer to think about when sort of thinking about personalized pricing, right? So there's another interpretation here where suppose I now have, and I'll have this in the next slide, suppose I now have a covariate here, right? So I say, this is my demand function for people who live in Ithaca, right? Or I have 10 more covariates, right? This is my demand function for someone who lives in New York in their late 20s or early 30s, or has this much income and so on, right? And so it's nicer to think about fractions there because then you can think about for each individual, you can interpret it as what's the probability that individual is going to buy an item, right? Because there's only like if you have enough covariates, there's only one person who matches that exact set of covariates. Any other questions here? Okay. Oops. Yeah. Okay. So how do we do demand estimation with multiple items? So last time, or maybe the time before, we suggested various machine learning approaches to learn sort of this demand function. And again, what I'm going to assume that we have some user with some covariates x of I. And now, sort of if we do the naive approach, we would need to estimate a different demand function for each item, right? So now you need to estimate demand 1 at price 1 and price 2 in these covariates, and demand 2 at price 1 and price 2 in these covariates, right? Or if you have 1 million models, then you would sort of need to sort of estimate 1 million different models here, or 1 million different items here. Sorry, if you have 1 million items, you'd have to estimate 1 million different models here. And this gets very hard very quickly, right? And so you would need to do this for every, like, let's say you have 1 million possible items, and each customer sees just 2 items, right? Then you would need to sort of estimate 1 million, choose 2, sort of like, so about 1 million squared set of items. Okay. And what's like some slightly more sophisticated approach? So now just use a multi-class classification algorithm. So instead of like logistic regression, do like a random forest that predicts classes, and like directly try to learn a function that tries to predict, given 2 prices and the user covariate, it either buys, what's the probability they buy item 1, item 2, and they buy nothing. And in scikit-learn, it's easy to extract these probabilities out of any classifier. So instead of like looking at just like the label that the classifier outputs, actually look at the classes, or sorry, look at the probabilities for each label. But this also gets a little bit tricky, because now, again, suppose you have 1 million different items, and you're just showing like pairs of these items to each user, right? So again, you would have to train about 1 million squared of these models, because you would have to train a unique model per pair of items. Or imagine you're not Netflix, but like Amazon doing sort of showing like 10 items on the front page out of their entire catalog of like a few, whatever, how many ever millions or billions of items, right? So they would have to do what, 1 million choose 10. So it's like some insanely large number of these models if they did that separately for each like possible combination of items. So instead, we can extend the idea that we sort of started talking about either last class or the class before, and also sort of use the idea from recommender systems, which is, suppose I have some user vector I for the user and some item vector for each item, right? So suppose I already, through browsing data, like this actually doesn't even have to come from purchase decisions, right? This can come from browsing data, where like Amazon knows, how many people added something to a cart even if they never purchased, or they know how many people clicked on the item or searched for an item with that result, or things like that, right? And so you can get user and item vectors even before any purchase decisions is made. And so instead of plugging in the sort of the user covariate X in this like model and like whatever, so this becomes a very large dimensional model, what you instead plug in is just my predicted ratings. So I plug in the dot product of the user vector dotted with the item vector. And so now, and then I have, 1 price for each, item 1 and item 2. And in theory, one can then start learning, and you can always add item-specific terms in this data as well. But what's nice here is now I'm training literally one model for all, even if I have 1 million items and I'm only showing 2 to each customer, instead of training 1 million square different models, I can train just one model. And then for any pair of items and a user, I just take the dot products of the user vector and the item vector, and I plug that in as my data. Does that make sense? Happy to answer questions here. Okay. So this is the last, oh yeah. Yeah, great question. So the question is if you have like 1 million items, but you don't have 1 million customers yet, then like how do you fit something like this? So I think that's actually one really nice aspect of the second. So certainly this like first model you just can't do, right? You can't fit this model for every sort of pair of users and items. But the second model, my claim is that you can still do, because what the second model is doing is that it's borrowing information across items, right? And so this has been, I think, a repeated theme of this class, where like sort of we had it in the polling or data collection things with sort of the method called MRP. We had it in recommendations when like learning these user and item vectors, and we have it again here, right? Is that what this thing is doing is we're learning just one model. We're learning one model that takes in the price for item 1, the price for item 2, and sort of some relationship between the item and the user. But it doesn't matter what the actual, like the identity of the item, because all we're looking at is the relationship through these vectors. And so if I had these vectors somehow, and so yes, so then the question is, how do I train these vectors if I have like no data right now? And here we can use some of the ideas for recommendation systems, right? Is I can train these user and item vectors for the users and items I've seen. And then to solve the code start problem for new users and new items that I haven't seen yet, I can use something like k-nearest neighbors, or I can sort of use the covariates I do have to guess at items and to guess at user and item vectors. Yeah, so these would be like the independent variables of a model. So these would be like the data into your model, and then to predict sort of this can go into a model that predicts the probability of buying each item. I guess the claim is that model kind of item agnostic. What is that model then trained? Yeah, so you could, let's suppose you have a bunch of training data that is, I showed this user this pair of items at these prices, and this is what they bought, right? And I had some item 1 and some item 2, but like sort of I labeled the items in whatever order, but the only thing that matters is their prices, like price 1 and price 2. And the only thing that matters is this dot product, right? So I have item 1, whatever item 1 can be like Harry Potter, it can be Lord of the Rings, it doesn't matter. The only thing that matters is the price I sold it at, and sort of this dot product between the user vector and the item vector. Exactly, yeah. Now, like sort of, I'm being a little hand wavy here in the sense that like you probably do also want like item specific variables. Like you do probably want like label specific, right? You probably do want like another code, like people just like pay for Lord of the Rings more than Harry Potter or something. So you do want like covariates that depend on the item as well. But sort of you can just like use that as like learn a single like offset for each item. But yeah, so your training data can be item agnostic, or the identity of the item agnostic, but just depend on the prices and these relationships. Any other questions here? Okay. Okay, so before moving on to like zooming out again on the pricing module, I do want to make a note on what we have covered with multiple items and what we haven't covered. So far, what we have is we have multiple items to sell that appeal to different customers, right? So business class versus economy class. And so here we have what's called items are substitutes, right? So items, if I buy one ticket, that makes me less likely to buy a second ticket, right? Or in this case, sort of what we assumed is if I buy one type of item, I'm definitely not going to buy the other type of item, right? So like one item substitutes for buying another kind of item. But often in practice, items, you can also have items that are complements to each other, which means if I buy one item, that makes me more likely to buy a different kind of item as well, right? So like if you go to a movie, like back when people used to go to movie theaters, soda and popcorn, right? So if I make popcorn cheap, then like someone might buy popcorn, but once they buy popcorn, they're like, okay, I also need a drink. Let me also buy a soda, right? So now the prices for popcorn, by lowering the prices for popcorn, you actually make it more likely that someone also buys soda. And Apple does this, of course, to great success, where they lock people into the ecosystem, and then as soon as they convince you to buy one item in that ecosystem, right, as soon as they convince you to buy an iPhone, they make it much more likely that you're also going to buy an iPad, an Apple Watch, a MacBook, everything else, right? All they need is to convince you to buy one item in their ecosystem, and then you're stuck. And yeah, so in this case, we sort of have the opposite effect that we talked. So what we talked about and sort of with those images was cannibalization, that lowering the price on one item made you less likely to buy the other item. But you could also have the opposite effect, which is lowering the price on one item might induce you to actually spend more money overall because now you're more likely to buy something else. And the term for this in business is often called a loss leader, which you have one item that sort of you're losing money on, but it's like your way to get your foot in the door to like get people to buy a bunch of other items, right? It's the standard like subscription coupons, all sorts of things. And you can go through a similar exercise that we went through. I'm not going to in this class, but you can go through a similar exercise to think about sort of what's the revenue maximizing prices. And there, sort of the demand estimation gets a little trickier because like now you might have to reason about sort of like demand over time, right? So like if I bought an iPhone already, what's the likelihood I buy an Apple Watch next month or something? And so like learning those demand functions in the presence of complements can get a little tricky. But in theory, sort of it might be something that you want to do depending on where you're at. Any questions here? Okay. Okay, so for the remainder, we have about 30 minutes left. For the remainder of the class, probably, I don't know how long this is going to take, maybe 10, 15 minutes, sort of talk through sort of putting the pieces together on recommendations and pricing. We've started doing some of that already with the demand estimation stuff I just talked about, but sort of putting more of these pieces together zooming back out to look at sort of cover everything that we've done in the pricing module so far, and sort of also start introducing and maybe getting y'all to think about the class competition. I'll post more details on this in the coming weeks, but I'll probably wait till like after homework 4 is out, and maybe like I assume no one's actually going to turn their attention to like doing stuff until after homework 4 is due. Okay. So far in this class, we've covered data collection and polling, but that's not really going to make a play a role in the class competition, the final project. But in recommendation systems, we covered given past user and item data, how much would each user like each new item that you haven't observed before? And then we talked about how to turn those predictions into recommendations, potentially in the presence of capacity constraints. And then in pricing, we've covered a bunch of different things. The first one was just single item revenue maximization. So if I have one item to sell to one person during one time period, how do I price that item? And then demand estimation, potentially with covariates, potentially with multiple items, and user and item vectors. And then also pricing over time with capacity constraints. And what I haven't covered, and I'm really not going to, is sort of the interaction between some of these things. Oh, sorry. Also pricing multiple items, right? So that was today. And what I haven't done, and I'm really not going to cover much in class, is like thinking about the interactions between these things, right? So in practice, you might have multiple items, each with some capacity that you're selling over time. That you might be selling in a personalized manner, or you might be pricing in a non-personalized manner. And so I'll briefly talk about these interactions of everything today in the context of, in the class project, you're going to be using all of these together. Sort of you're going to be doing pricing in the presence of all of these effects, in the presence of all of these potential data sources. Okay. So suppose, and what we also haven't covered in class at all so far, but that's going to play a big role, is competition. So what's like the high level model? Suppose you and a single competitor, which in this case will be your sort of one other team from the class, are each trying to sell two types of items. So you have a book A and a book B. And let's say you have some initial capacity. For the example, let's just say you have 10 of each book 1 and book A and book B. And a customer walks in, and you're going to observe some of their personal data. So you might observe their demographic covariates. You might also observe their demographic covariates as well as user and item vectors, or user vectors trained on sort of past, like that person's been on your website before. So you might also observe user vectors. And then you and your competitor are going to post prices for each item. So each of you is going to decide a price for book A and a price for book B. And the customer buys at most one item, and then they leave. And how are they going to choose which item to buy? They're going to choose which item to buy based on the model that I presented earlier in class. Right now they have sort of 4 possible utilities. Right, so if they buy book A from you, then it's going to be their utility is the value for book A minus the price that you set for book A. If they buy book B from your competitor, that's going to be the value for their value for book B minus the price that your competitor set for book B, right? So you have 4 of those utilities. They just pick the best one, and that's what they do. Or if none of those are above 0, then they don't buy anything. And then we're going to repeat this for many customers over time, right? So let's say we have 100 or 1,000 of such customers walking in over time. And you could imagine that this is exactly sort of like a simplified version of what, maybe, so I'll talk about ride hailing in particular next week, hopefully, but sort of this is almost exactly what like maybe Uber and Lyft are doing, right? So like the same customer can open both app and Uber and Lyft will observe similar data about the customer, or what sellers on Amazon. So Amazon, I think at the moment doesn't support personalized prices for like a random seller. That like a random seller selling something on Amazon can do personalized prices, but you could imagine um, sort of like like sort of online retailers that do approximately do personalized prices, for example, through coupons. And this is a simplified model of like that real world setting. Yeah, so the question is, can you observe the competitor prices? So, certainly not after you like until you make your pricing decision. So like everyone posts their prices simultaneously. I think I will give you that information. So I think sort of like the way this is going to be annoying for me to code up, but like y'all are gonna like give me your trained models, and I'll give some instructions for how to give the trained models, and then we'll do like I'll use OpenAI Gym or something if y'all have used that before to like sort of each iteration I'll like give you some covariates, we'll get the prices, and then I'll return to you the reward and potentially the prices that your competitor set, and like who ended up sort of getting the sale that round. And then it'll be iterative, right? So like I'll just like do a for loop and do that for 1,000 time periods. Any other questions for the basic setup? Yes, yeah. So the goal will be yes. So the goal will be sort of the winner of a single round will be the person who gets the most revenue, right? So if I wanted to just maximize the number of sales, I would just put everything at 1 cent, right? Okay. And so I think for the rest of class, I'm going to walk through sort of like how would we like go about like this has a many moving parts, and like many moving parts that like tries to connect everything that we've done in class so far. And so I'll maybe break down sort of the approach one would take to start building up a solution like this, which might be like sort of hopefully the thought process one would go through to like build up first a naive solution in practice, and then build up to like factor in more and more things. Yeah, so the question is, how does the customer make their decision? And so basically what I'm going to have is so that sort of internally what I'm not going to expose to you is the customer has some valuation. And so like in the current homework that you're doing, the sort of I gave you some past data that was generated like this, where the customer had some internal valuation that you never see. And then in the homework, you just see the outcome at different, like sort of this customer was offered this price and either purchased or didn't, right? So here we're going to have the customer is going to have some hidden valuation for item A and item B, for book A and book B. And this valuation is, of course, is going to correlate with the covariates that you're given. But literally in what we're going to do is sort of given the, like we have access to these valuations, we're just going to calculate the 4 utilities, right? We're going to calculate value for book A minus the price you set, value for book A minus the price your competitor sets, value for B minus the price you set for B, and so on. And then so we have 4 numbers. If all 4 of those numbers are less than 0, then they're not going to buy anything. Otherwise, they're going to buy the maximum, right? So it's an extension of the model that we talked about in class with just 2 items and like 2 prices.
In terms of like judging it, is it siloed between your individual competitors? So like make like $1 versus a competitor. Is it just a comparison between those two, or is it like a formula structure? Total profit overall.
I'll give all of those details in a later time. Right now, I just want to focus on like sort of the more substance, like bring together the pieces we've talked about in class. I'll give like a lot more details on the structure later on. Any other questions? Okay. Okay, so how would we go about doing this given everything that we've covered in class so far? So for now, and this is, the first thing one does in practice is ignore competition, because competition makes everything really hard. So let's ignore competition, and let's also ignore capacity constraints, right? So suppose each time a customer comes, you can set whatever price you want. Sort of like you don't have to think about future time. So for each user, you either just have their demographic covariates X, or you also have a trained user vector from past interactions on your site. Then you can predict the demand for each item given all of this data. And we talked about, for example, sort of a few slides ago, we talked about how one would do this for multiple items, and potentially using and sending in the dot product of xi and UI, or sort of sending the dot product of the user vector and the item vector, as opposed to like sending in the full user vector. You're going to make some choice on how to estimate this demand. And you're also going to make some choice on what to do for customers where you don't have a user vector U. Right? And so, like so far in the the homework certainly has depending on your programming experience and sort of how comfortable you are with pandas, the homework certainly haven't been easy, but they've been straightforward in the sense that we mostly told you like do this and then do that for each step. Here now, you're going to be left completely on your own in the sense of like what choices to make on like how to do this demand estimation, and what do you do for customers with no user vector. And ideally, you would use some of the ideas that we talked about in class and in home, and like y'all practice in the homework. Okay, so you do this demand estimation, and then ignoring competition and capacity constraints, you would just set prices that maximize your expected revenue. Okay, so what's the first complication? The first complication is that, okay, so for example, let's pretend that you have just 10 copies of each item, and you have 100 customers will come over time. So now you have capacity constraints, right? You can't sell more than 10 items total, 10 times. You can't sell book A more than 10 times. So now the price that you set should depend on the future opportunity cost, right? If I sell this item at this price right now, what money could I have made in the future to sell that item to a different customer? And what's tricky here, and I'll sort of dig into this in a little bit more. What's tricky here is that so far, when I talked about writing this dynamic program, this Bellman equation, sort of, and setting prices, so far, what I talked about was not in the sense of personalized prices, right? So that you just, no matter which customer walks in, you're going to set some price P of 10, some price P at day 10, some price at day 9, some price at day 8. But now, the prices that I set in the future are going to depend on customers who haven't shown up yet. But actually, even before we get to that, how would you sort of, even just given what we've talked about in class, how would you do this? So last class, I briefly talked about doing a two-dimensional dynamic program where you also had capacity for item 1, for just like one item. And in the homework, I think one of the bonus questions is to exactly implement I think one of the mandatory questions is sort of writing out this dynamic program and optimizing prices over time if you have just one copy of the item. But I think one of the bonus questions is if let's suppose you had 5 copies of the item, how would, right? So there you had what's called a two-dimensional dynamic program, where at each time you had different time steps, but you also had different number of items left, right? You could have 5 copies left, or 4 copies left, or 3 copies left, and the prices would be different. Okay, so here, even without thinking about competition, we have a three-dimensional dynamic program, right? You have, at each time period, you could have the capacity of book A left, some capacity for book A, and some capacity for book B.
You assume that you know something about the customers that are coming in the future.
Great question. So I'm about to talk about that in a second. Yeah. So, okay. So, yeah, but sort of, yeah, I'll talk about that in a second. But yeah, so you have now a three-dimensional dynamic program. And so how do you set it up? My value for each time period. So now I have a value at time t. If I have capacity Ka for book A and capacity Kb for book B. And this is sort of, you could break this up into 3 parts. I'm not going to write out the full equation, but you could break this up into 3 cases. The first case is, if I sell book A today, how much money do I make today? Plus, how much money do I make in expectation in the future if I have 1 less copy of book A? Same thing for book B. And then same for C, which is if I don't sell anything, how much money do I make in the future given the same number of copies? All right, so I could write this equation down, and then given sort of, given the other value, given like v of t plus 1 and all of these other values, I can write it, I can do an optimized price for this time period. Okay, and so related to your question, the question is, how do I calculate this future revenue, right? So what I need to care about is my revenue today sort of depends on my prices today, but also expected future revenue. If I don't sell the item today, how much money can I make on average tomorrow? And so what did we talk about last time? What we talked about last time is the way to do this is you would think backwards. So first you would think about, here's the prices I would set on the last day, day 99, for each combination of capacities left, right? So if I have, on the last day, if I have 10 of each item left, if I have 9 of each item left, if I have 10 of one, 6 of the other, and so on. And then I would think about, okay, what prices would I set on the last day? But now the complication, which is exactly what you just asked about, which is my prices on the last day depend on the customer who's going to show up on the last day, right? Like if a customer has high valuation for book A, then I'm going to give a high price for book A. If they have a low valuation, I'm going to give them a low price. But on day, let's say 5, I don't know who's going to show up on day 99. I don't know the future. Right? You only know the customers who've shown up today and all the times before today. And so when calculating this future expected value, you need to consider sort of the distribution of customers who can show up, right? A customer with this valuation, with like these covariates is going to show up with this probability. A customer with that covariates is going to show up with that probability. And you can do this because I'm going to give you a bunch of training data that like sort of gives you the distribution of customers. And there's a bunch of sort of machine learning tricks that like maybe I'll like give reading resources on how to sort of do this well. But sort of the idea is that your future value now depends on sort of the future revenue, expected revenue depends on like a random customer who's going to show up in the future. So your future valuations depend on sort of is like now like something you can't calculate exactly, but you can calculate an expectation by like thinking about what are all the combinations of who can show up.
one less person coefficient shows up. Like I don't know. Like if you know it's a fixed size of people and you know your covariance correctly.
Yeah, so the question is would you write a Bellman equation that has like who shows up in the sort of in the thing? Not exactly, because sort of like at the end of the day, sort of I'm setting the price for today, right? I need to set a price for today. And to do that, I need like some revenue on average tomorrow if I have 10 items left. Like I don't know which customer is going to show up tomorrow. And so if I have a different entry in like my table for each, like for expected revenue tomorrow if this person shows up, or revenue tomorrow if that person shows up, and so on, I don't know which of those values to use when calculating price today. Yeah. And so you really need to calculate the average of those and use that as your value. No, I'm going to just make a constant distribution over time.
So here we care about time. I guess in most contexts too, there's like a promotional sale or a campaign or what have you. But for cases where it's like maybe a commoditized product, yeah, granted, maybe for $1,399 you have a promotion, but macro level, there is no like T is kind of infinite, and capacity, yeah, you have operational. Okay, ignore capacity, but just in terms of time, how do they kind of approach the problem for things that are always on sale but also always sold? Like there's always a car sale, but
Yeah, so there with like sort of these things where there's so the question is like, how do you reason about things where there's no like deadline, right? There's no time t in which the game ends. So there you can think about like there's no fixed time t at which the game ends, but like even for something like, okay, so maybe not soap, and like people are going to be annoyed if you do dynamic pricing for soap, but like something like cars, this is definitely true, right? Is you can think about when is my next shipment going to come in for cars, right? And so if on day, I know that my next shipment's going to come 2 months from now, then I do need to like I do have in some sense a fixed capacity for the next 2 months, and then then more items will come in, and so like I'll be replenished in about 2 months or something. And so then you could like think about there's ways to extend this to like infinite time if like with replenishment of capacities and things like that. But there you need to start doing what's called discounting, which is like you can't have that a dollar today is worth the same as a dollar 20 years from now, because you're probably going to be out of business 20 years from now. So you need to like value and inflation and blah blah blah. And so you need to value a dollar today more than you value a dollar 20 years, like making that same dollar 20 years from now. And that actually makes the math easier too, is because you can like at some point you can ignore everything that happens after 10 years, because like or like 20 or some amount of time you can just start ignoring it, because like you'd rather just make the dollar today. Any other questions here? Okay. And so yeah, so you would use the training data that we give you to consider the possible customers who could show up, and then calculate your expected revenue in that way. Yeah, right. Then you would calculate, here's the prices I would show to someone on day 500 or day 100 if that's who showed up, and then like sort of average over my revenue for on day 100. Okay, so that's the first complication, which is thinking about capacity constraints over time. And then the second complication, which I'm basically going to like spend very little time on in this class, I might give some reading resources, but like I think this is going to, maybe I'll spend a little bit more time later on, but I think this will be a core part of the competition. I just want you all to like think about how to do pricing in this setting, which is, so suppose you and your opponent, which sat in the same class, have access to the same data, sort of have learned similar methods. Both do the same thing, and suppose y'all end up calculating very similar prices or the exact same price, right? But your opponent is clever, and so decides to undercut you a little bit, right? So says that instead of setting price A and price B, I'm going to set 1 cent cheaper for each book A and book B, and then they're the ones who are going to get the sale, right? So the customer is going to buy from whichever one of these items because it's 1 cent cheaper. But maybe you're even more clever, and so you say, okay, I know my opponent is clever and is going to undercut me by a cent, so let me undercut them by 2 cents. And then you can think about sort of like how this ends up. And so this is sort of what's sort of like the way to reason through this is what's called game theory, which is you need to anticipate what your opponent is going to do when you're setting these prices. And so you go through the entire process that I talked about through the last slide, and you end up with some price A and some price B. And now you need to think about, okay, how do I actually get the sale because the customer might also buy from my opponent. And this gets more complicated because now what we're doing is we're doing a repeated setting, right? So what does a repeated setting mean? Is if I lose today, your competitor has less, has one less item in stock for tomorrow. And so maybe, one perfectly viable strategy could be that I just let my competitor win the first 20 time periods, deplete all their stock, and then I make a bunch of money in the future. I don't know how that would work out. What if if you and your competitor both try doing this? But yeah, so this repeated setting matters, and now you care about revenue at the end. But sort of, it's also nice in that you can try to learn how your opponent behaves. So in the experimentation section, I'm going to talk a little bit about adaptive policies that sort of like you're learning parameters like about the environment that you're in. And so in this setting, you can try to learn parameters about how your opponent is behaving, right? So for example, you can maybe have some parameter alpha that says how much I subtract from my prices. And each time step, depending on if alpha was big enough, you can decrease alpha or increase alpha, right? And so that's, in some sense, learning a model for how your opponent is behaving and how much you need to give discounts as a result. Yeah, so you'll start out with the same stock, but then if you deplete yours and your opponent doesn't, then like on time 500, like in time 50, you might not have the same stock, but at time 0, you will. Yes, exactly. Yeah, so you could imagine, for example, so like the Bellman equation that I wrote down is 3-dimensional. You could also imagine making that 5-dimensional, right? So now per time and then per 4 stocks that you and your competitor have.
What happens when me and my opponents offer the same price?
I haven't thought about that. I mean, probably they'll do random. Yeah. So they'll just flip a coin with probability with 50-50. I mean, odds are you're not going to, because like we'll allow you to like submit 10 decimal places or something for the price. So like it would be very unlikely, but yes. Then you just flip a coin. Yeah.
Something like thinking about like price gouging legal in our.
Yeah. So the price gouging is legal. Everything's legal. Yeah, so the question is like what real life scenario does this map onto? Or roughly, so like, while explaining this, I said books, but like there's like aspects of this that like, map onto different real life scenarios. So for example, you can think about Uber and Lyft, where Uber and Lyft are doing something very similar. I mean, I don't know how much they're like modeling competitor prices and doing that, but you can imagine in theory they could be, right? Is that like I want to go from here to somewhere, I open up both apps at the same time, I tell them I'm going to the same place, and then like, you know, I've used both of them in the past, so they have some data on me each, and then they each set their prices, and then I set the lower, right? And so in the competition to make your lives easier, I might give you more information than like Uber and Lyft have, right? Like Uber and Lyft don't directly observe each other's prices. They don't directly observe how many drivers the other one has access to. But like here in this setting, like I'll just give that to you. And you can also imagine like retail, like, you know, different sellers, again, different sellers on Amazon. So like Amazon, I think, again, directly doesn't do allow personalized pricing for marketplace sellers. But you can imagine, except for the personalized price, this is exactly the scenario that different sellers on Amazon face, right? They have some quantity of an item to sell, and there's a bunch of copycats on Amazon. Okay. So I think that is time. So I think I'm gonna wrap up here. I'm happy, like, you know, I'm gonna talk about more, I'm gonna release more things about the competition in the future. Today, I just wanted to use this as like, talk about bringing all the pieces together for pricing. The reminder is, so next time we're gonna have an in-person class on, you know, a discussion-based class on what's acceptable in pricing. Please come in person, I will be taking attendance. It's not, whether or not it's recorded, sort of, I don't know, but it's not gonna be posted online. So yeah, so like, and yeah, so please come in class on Monday. And please do the questionnaire as part of the homework before class on Monday. Cool.